Hello everyone, welcome. This is chemistry topic thermodynamic process. Worked example topic 1 adiabatic process. I am Omenka Fivo Ogbu. You can reach me on the following email, either the Gmail or the Yahoo. Please, if you coming across this channel Ogbu Omenka for the first time, please do well to click on the subscribe button. You have been around and you haven't subscribed, please do well to subscribe. Thank you. The objective of the study is understand the concept of an adiabatic process and its characteristics. Lesson outline: solve simple problems based on an adiabatic process. The lesson outcome: after the lesson, you should be able to analyze and calculate basic questions relating to adiabatic process in thermodynamics. Adiabatic process. An adiabatic process is a thermodynamic process where there is no exchange of heat in between the system and its surroundings. This means that no heat energy is added to or removed from the system, although the temperature of the system may still change due to internal energy transfer or work done on the system. This is an illustration of the work done on a system, and what happened here is that you have the system and you have the surrounding. So there is going to be a what we call expansion and compression on the system. This is if this piston happens to go down. Therefore, there is going to be work done on the system. It's going to lead to compressions. However, if the piston happens to move up, then it's going to be work done by the system, which is lead to expansions. Something like this as illustrated. Yes. Examples of adiabatic process include compression of a gas cylinder. That is, the compression of a gas cylinder is one of the examples of adiabatic process. Then expansion of gas in a balloon. Adiabatic process equations include PV to the power of gamma is equals to constant. Then P to the power of 1 minus gamma. T to the power of gamma is equals to constant. T to the power TV to the power of gamma minus 1 is equal to constant, where gamma is equals to Cp all over Cv. P is the pressure, V is the volume, T is the temperature, gamma is the adiabatic index, Cp is the heat capacity at constant pressure, Cv is the heat capacity at constant volume in reversible adiabatic process. Show that W is equal to R to bracket T2 minus T1 all over 1 minus gamma, where W is work done, R is the molar gas constant, T2 is the final temperature, T1 is the initial temperature, gamma is the adiabatic index. Recall that PV to the power of gamma is equals to constant. Differentiating these equations using this method of differentiation, which includes x to the power of n, you use this power to multiply by the coefficient, then you subtract 1 from the power. Therefore, you have it to be what? You are differentiating this, you have it to be x to the power of n is equals to what? N x to the power of n minus 1 gives. So if you keep the P constant, you differentiate V. So differentiating V now, the gamma multiplied by the coefficient, which is 1. So you have it to be what? Gamma P V. Then you subtract 1 from the gamma. You have it to be what? Gamma minus 1. Then the V, because you are differentiating with respect to what? V, keeping P constant. Then plus, you keep V to the power of gamma constant, then differentiate p, then is equal to 0, because if you differentiate constant, you're going to have it to be equal to what? 0. This is also from the product rule of differentiation. Multiply all through by v gives gamma pv to the power of gamma minus 1 times v dv plus v times v to the power of gamma dp is equal to 0. From the laws of indices, if we are dividing and the bases are the same, you pick one of the bases, then you subtract the powers. This is how it comes about v to the power of gamma minus 1. So bringing it back now, have it to be gamma p times v to the power of gamma all over v times v dv plus v times v to the power of gamma dp is equal to 0, so that v and v can cancel out and the expression will reduce to gamma p v to the power of gamma dv plus v times v to the power of gamma dp is equal to 0. Divide all through by v to the power of gamma gives gamma p times v to the power of gamma all over v to the power of gamma, so that v to the power of gamma can be divided by v to the power of gamma, then dv plus v times v to the power of gamma all over v to the power of gamma to cancel out, times dp is equal to 0. So the equation reduces to gamma p dv plus v dp is equal to 0. Subtracting gamma p dv from both sides gives v dp is equals to minus gamma p dv. Number it as equation I or equation 1. For 1 mole of an ideal gas, PV is equals to RT. Differentiating PV equal to RT gives, you keep P constant, differentiate V, plus keep V constant, differentiate P is equals to keep R constant, differentiate T, plus keep T constant, differentiate R. So since R is the molar gas constant, is a constant, if you are differentiating a constant, is going to be equal to 0. So the whole of this one is going to be out. It's going to be what? Equal to 0. So the expression reduces to P dV plus V dP is equals to R dt. Subtracting P dV from both sides gives V dP is equals to R dt minus P dV. Number it as equation. Substituting equation 2 into equation 1, we put this equation 2 into this equation 1 gives R dt minus P dV is equals to minus gamma P dV. Adding P dV to both sides gives R dt is equal to P dV minus gamma P dV. Factorizing P dV out gives R dt is equals to, you factorize out because P dV is common here and P dV is common here, so you factorize it, you bring it out. Therefore, you have it to be, if you have P dV divided by P dV, you are left with 1. You write it in a bracket, then minus gamma P dV divided by P dV, you are left with minus gamma. You write it in a bracket like this. Divide all through by 1 minus gamma gives R dt all over 1 minus gamma is equals to P dV. Recall that P dV is equals to dW. Therefore, dW will be equal to R dt all over 1 minus gamma. Integrating the expression gives W is equals to R all over 1 minus gamma. R all over 1 minus gamma These are constants, so you keep them outside the integral sign. Then while you take the integral from the limit from t2 to t1, then the t, so it gives w is equals to r all over 1 minus gamma times the bracket t2 minus t1. Therefore, we have our expression finally to be w is equals to r into bracket t2 minus t1 all over 1 minus gamma.